Okay, cameras are rolling. This is lecture 14, starting a new chapter. Chapter about orthogonality, what it means for vectors to be orthogonal, what it means for subspaces to be orthogonal, what it means for bases to be orthogonal. So 90 degree, this is a 90-degree chapter. So what does it mean? Let me jump to subspaces, because I've drawn here the big picture. This is the 1806 picture here. And hold it down, guys. So this is the picture, and we know a lot about that picture already. We know the dimension of every subspace. We know that these dimensions are R and n minus R. We know that these dimensions are R and m minus R. What I want to show now is what this figure is saying, that the angle, but the figure is like just my attempt to draw what I'm now going to say, that the angle between these subspaces is 90 degrees. And the angle between these subspaces is 90 degrees. Now I have to say, what does that mean? What does it mean for subspaces to be orthogonal? But I hope you appreciate the beauty of this picture, that those subspaces are going to come out to be orthogonal. Those two and also those two. So that's like one important point to step forward in understanding those subspaces. We knew what each subspace was like. We could compute bases for them. Now we know more, or we will in a few minutes. Okay, I have to say, first of all, what does it mean for two vectors to be orthogonal? So let me start with that. Orthogonal vectors. The word orthogonal is just another word for perpendicular. It means that in n-dimensional space, the angle between those vectors is 90 degrees. It means that they form a right triangle. It even means that, going way back to the Greeks, that this triangle, a vector x, a vector y, and a vector x plus y, of course, that'll be the hypotenuse. So what was it the Greeks figured out? And it's neat. It's the fact that so these are orthogonal. This is a right angle if, so let me put the great name down, Pythagoras. I'm looking for, what am I looking for? I'm looking for the condition, if you give me two vectors, how do I know if they're orthogonal? How can I tell two perpendicular vectors? And actually, you probably know the answer. Let me write the answer down. Orthogonal vectors, what's the test for orthogonality? I take the dot product, which I tend to write as x transpose y, because that's a row times a column, and that matrix multiplication just gives me the right thing, that x1, y1 plus x2, y2, and so on. So these vectors are orthogonal if this result, x transpose y, is 0. That's the test. Okay. Can I connect that to other things? I mean, it's amazing. It's just beautiful that here we're in n dimensions. We've got a couple of vectors. We want to know the angle between them. And the right thing to look at is the simplest thing that you can imagine, the dot product. Okay. Now, why? So I'm answering the question now, why? Let's add some justification to this fact that that's the test. Okay. So Pythagoras would say we've got a right triangle if that length squared plus that length squared equals that length squared. Okay. Can I write it as x squared plus y squared equals x plus y squared? Now please don't think that this is always true. This is only going to be true in this, it's going to be equivalent to orthogonality. For other triangles, of course, it's not true. For other triangles, it's not. But for a right triangle, somehow that fact should connect to that fact. Can we just make that connection? What's the connection between this test for orthogonality and this statement of orthogonality? Well, I guess I have to say, what is the length squared? So let's continue on the board underneath with that equation. Give me another way to express the length squared of a vector. Let me just give you a vector. The vector 1, 2, 3. That's in 3 dimensions. What is the length squared of the vector x equal 1, 2, 3? So how do you find the length squared? Well, really, you want the length of that vector that goes along 1, up 2, and out 3. And we'll come back to that right triangle stuff. The length squared is, this is exactly x transpose x. Whenever I see x transpose x, I know I've got a number that's positive. It's a length squared. Unless x happens to be the 0 vector, that's the one case where the length is 0. So, right, this is just x1 squared plus x2 squared plus so on plus xn squared. So in the example I gave you, what was the length squared of that vector 1, 2, 3? So you square those, you get 1, 4, and 9. You add, you get 14. So the vector 1, 2, 3 has length 14. So let me just put down a vector here. Let x be the vector 1, 2, 3. Let me cook up a vector that's orthogonal to it. So what's the vector that's orthogonal? So write down here, x squared is 1 plus 4 plus 9, 14. Let me cook up a vector that's orthogonal to it. We'll get right? That those two vectors are orthogonal. The length of y squared is 5. And x plus y is 1 and 2 making 3, 2 and minus 1 making 1, 3 and 0 making 3. And the length of this squared is 9 plus 1 plus 9, 19. And sure enough, I haven't proved anything. I've just checked to see that my test x transpose y equals 0, which is true, right? Everybody sees that x transpose y is 0 here? That's maybe the main point, that you should get really quick at doing x transpose y. So it's just this plus this plus this, and that's 0. And sure enough, that clicks with 14 plus 5 agreeing with 19. Now, let me just do that in letters. So that's y transpose y. And this is x plus y transpose x plus y. Okay. So I'm looking, again, this isn't always true. I repeat. This is going to be true when we have a right angle. And let's just, well, of course, I'm just going to simplify this stuff here. There's an x transpose x there. And there's a y transpose y there. And there's an x transpose y. And there's a y transpose x. I knew I could do that simplification because I'm just doing matrix multiplication and I've just followed the rules. Okay, so x transpose x's cancel, y transpose y's cancel. And what about these guys? What can you tell me about the inner product of x with y and the inner product of y with x? Is there a difference? I think while we're doing real vectors, which is all we're doing now, there isn't a difference. There's no difference. If I take x transpose y, that'll give me 0. If I took y transpose x, I would have the same x1, y1, and x2, y2, and x3, y3. It would be the same. So this is the same as that. This is really, I'll knock that guy out and say 2 of these. So actually, that's this equation boiled down to this thing being 0, right? Everything else canceled, and this equation boiled down to that one. So that's really all I wanted. I just wanted to check that Pythagoras, for a right triangle, led me to this. Of course, I cancel the 2 now, no problem, to x transpose y equals 0 as the test. Fair enough. Okay. You knew it was coming. The dot product of orthogonal vectors is 0. It's just, I just want to say, that's really neat. It comes out so well. All right. Now, what about, so now I know what it means when 2 vectors are orthogonal. By the way, what about if one of these guys is the 0 vector? Suppose x is the 0 vector and y is whatever. Are they orthogonal? Sure. In math, the one thing about math is you're supposed to follow the rules. So you're supposed to, if x is the 0 vector, you're supposed to take the 0 vector dotted with y, and of course, you always get 0. So, just so we're all sure, the 0 vector is orthogonal to everybody. But what I now want to speak about is subspaces. What does it mean for me to say that some subspace is orthogonal to some other subspace? So, okay, now I've got to write this down, because we're defining definition of subspace S is orthogonal, so to subspace, let's say T. So I've got a couple of subspaces. And what should it mean for those guys to be orthogonal? It's just sort of, what's the natural extension from orthogonal vectors to orthogonal subspaces? Well, and in particular, let's think of some orthogonal subspaces, like this wall. Let's say in 3 dimensions. So the blackboard extended to infinity, right, is a subspace, a plane, a 2-dimensional subspace. It's a little bumpy, but anyway, think of it as a subspace. Let me take the floor as another subspace. Again, it's not a great subspace. MIT only built it like so, but, and I'll put the origin right here. So the origin of the world is right there. Okay. Thereby giving linear algebra its proper importance in this. Okay, so there's one subspace, there's another one, the floor. And are they orthogonal? What does it mean for two subspaces to be orthogonal? And in that special case, are they orthogonal? All right, let's finish this sentence. What does it mean? Means. We have to know what we're talking about here. So what would be a reasonable idea of orthogonal? Well, let me put the right thing up. It means that every vector in S, every vector in S is orthogonal to, what am I going to say? Every vector in T. That's a reasonable, and it's a good, and it's the right definition for two subspaces to be orthogonal. But I just want you to see, hey, what does that mean? So answer the question about the blackboard and the floor. Are those two subspaces, they're two-dimensional, right? And we're in R3. It's like the xz plane or something and the xy plane. Are they orthogonal? Is every vector in the blackboard orthogonal to every vector in the floor? Starting from the origin right there. Yes or no? I could take a vote. Probably get some yeses and some no's. No is the answer. They're not. You can tell me a vector in the blackboard and a vector in the floor that are not orthogonal. Well, you can tell me quite a few, I guess. Maybe, like, I could take some 45-degree guy in the blackboard and some thing in the floor that aren't at 90 degrees, right? In fact, even more, you could tell me a vector that's in both the blackboard plane and the floor plane, so it's certainly not orthogonal to itself. So for sure, those two planes aren't orthogonal. What would that be? So what's a vector that's in the in both of those planes? This guy running along the crack there, where the intersection. A vector. Look, if two subspaces meet at some vector, well then for sure they're not orthogonal because that vector is in one and it's in the other and it's not orthogonal to itself unless it's zero. So so orthogonal, if for me to say these two subspaces are orthogonal, first of all, I'm certainly saying that they don't intersect in any non-zero vector. But also, more than that, just not intersecting isn't good enough. So give me an example. Oh, let's say in the plane. Oh, well, when do we have orthogonal subspaces in the plane? Yeah, tell me in the plane. So there aren't that many different subspaces in the plane. What have we got in the plane as possible subspaces? The zero vector, real small, a line through the origin, or the whole plane. Okay. Now, so when is a line through the origin orthogonal to the whole plane? Never, right? Never. When is a line through the origin orthogonal to the zero subspace? Always. When is a line through the origin orthogonal to a different line through the origin? Well, that's the case that we all have a clear picture of. The two lines have to meet at 90 degrees. They have only the, so that's like this simple case I'm talking about. There's one subspace, there's the other subspace. They only meet at 0, and they're orthogonal. Okay. Now, so we now know what it means for two subspaces to be orthogonal, and now I want to say that this is true for the row space and the null space. Okay, so that's the neat fact. So row space is orthogonal to the null space. Now, how did I come up with that? But you see, it's great. That means that these subspaces are just the right things. They're just cutting the whole space up into two perpendicular subspaces. Okay, so why? Well, what have I got to work with? All I know is the null space. The null space has vectors that solve A, x equals 0. So this is a guy x. X is in the null space. Then ax is 0. So why is it orthogonal to the rows of A? If I write down ax equals 0, which is all I know about the null space, then I guess I want you to see that that's telling me, just that equation right there is telling me that the rows of A, let me write it out. There's row 1 of A. Row 2. Row M of A. That's A. And it's multiplying x, and it's producing 0. Okay. Written out that way, you'll see it. So I'm saying that a vector in the row space is perpendicular to this guy x in the null space. And do you see why? Because this equation is telling you that row 1 of A multiplying, that's a dot product, right? Row 1 of A dot product with this x is producing this 0. So x is orthogonal to the first row and to the second row. Row 2 of A, x is giving that 0. Row M of A times x is giving that 0. So the equation is telling me that x is orthogonal to all the rows. Right? It's just sitting there. That's all it had to be sitting there because we didn't know anything more about the null space than this. And now I guess to be totally complete here, I've now checked that x is orthogonal to each separate row. But what else, strictly speaking, do I have to do? To show that those subspaces are orthogonal, I have to take this x in the null space and show that it's orthogonal to every vector in the row space. Every vector in the row space. So what else is in the row space? This row is in the row space. That row is in the row space. They're all there. But that's not the whole row space, right? We just have to remember, what does it mean? What does that word space telling us? And what else is in the row space besides the rows? All their combinations. So I really have to check that, sure enough, if x is perpendicular to row 1, row 2, all the different separate rows, then also x is perpendicular to a combination of the rows. And that's just matrix multiplication again. You know, I have row 1 transpose x is 0. So on. Row 2 transpose x is 0. So I'm entitled to multiply that by some C1, this by some C2. I still have zeros. I'm entitled to add. So I have C1 row 1. So all this, when I put that together, that's big parentheses, C1 row 1 plus C2 row 2 and so on. Transpose X is 0. Right? I just added the zeros and got 0, and I just added these following the rules. No big deal. The whole point was right sitting in that. Okay. So, if I come back to this figure now, I'm like a happier person because I have this, I now see how those subspaces are oriented. And these subspaces are also oriented. Well, actually, why is that orthogonality? Well, it's the same statement for A transpose that one was for A. So I won't take time to prove it again because we checked it for every matrix, and A transpose is just as good a matrix as A, so we're orthogonal over there. So we really have carved up this was like carving up m-dimensional space into two subspaces, and this one was carving up n-dimensional space into two subspaces. And, well, one more thing here. One more important thing. Let me move into 3 dimensions. Tell me a couple of orthogonal subspaces in 3 dimensions that somehow don't carve up the whole space. There's stuff left there. I'm thinking of a couple of orthogonal lines. If I suppose I'm in 3 dimensions, R3, and I have one line, one-dimensional subspace, and a perpendicular one. Could those be the row space and the null space? Could those be the row space and the null space? Could I be in 3 dimensions and have a row space that's a line and a null space that's a line? No. Why not? Because the dimensions aren't right? The dimensions are no good. The dimensions here, r and n minus r, they add up to 3. They add up to n. If I take, if I just follow that example, if the row space is one-dimensional, suppose A is, what's a good, I'm in R3, I want a one-dimensional row space. Let me take 1, 2, 5, 2, 4, 10. What's the dimension of that row space? 1. What's the dimension of the null space? What's the null space look like in that case? The row space is a line, right? One-dimensional. It's just a line through 1, 2, 5. Geometrically, what's the row space look like? It's a, what's its dimension? So here n is 3. The rank is 1. So the dimension of the null space, I'm looking at this x, x1, x2, x3, to give 0. So the dimension of the null space is, we all know is 2. Right, it's a plane. And now actually we see better what plane is it. What plane is it? It's the plane that's perpendicular to 1, 2, 5. Right? We now see. In fact, the 2, 4, 10 didn't actually have any effect at all. I could have just ignored that. That didn't change the row space or the null space. I'll just make that one equation. Yeah, okay, sure. That's the easiest to deal with. One equation, three unknowns, and I want to ask, what does the equation give me? It gives me the null space, and you would have said, back in September, you would have said it gives you a plane, and we're completely right. And the plane it gives you, the normal vector, you remember in calculus there was this normal vector called n. Well, there it is, 1, 2, 5. Okay. So, what's the point I want to make here? I want to emphasize that not only are let me write it in words. So I want to write the null space and the row space are orthogonal. That's this neat fact, which we just checked from AX equals 0. But now I want to say more, because there's a little more that's true. Their dimensions add to the whole space. So that's like a little extra information. It's not like I couldn't have a line and a line in 3 dimensions. Those don't add up. 1 and 1 don't add to 3. So I use the word orthogonal complements in Rn. And the idea of this word complement is that the orthogonal complement of a row space contains not just some vectors that are orthogonal to it, but all. So what does that mean? That means that the null space contains all, not just some, but all vectors that are perpendicular to the row space. Okay. Really what I've done in this half of the lecture is just notice some of the nice geometry that we didn't pick up before because we didn't discuss perpendicular vectors before. But it was all sitting there, and now we've picked it up, that these vectors are orthogonal complements. And I guess I even call this part 1 of the fundamental theorem of linear algebra. The fundamental theorem of linear algebra is about these 4 subspaces. So part 1 is about their dimension. Maybe I should call it part 2 now. Their dimensions we got. Now we're getting their orthogonality. That's part 2. And part 3 will be about bases for them, orthogonal bases. So that's coming up. Okay. So I'm happy with that geometry right now. Okay. Okay. Now what's my next goal in this chapter? It's the main problem of the chapter. The main problem of the chapter is, so this is coming attraction. This is the very last chapter that's about AX equal B. I would like to solve that system of equations when there is no solution. You may say, what a ridiculous thing to do, but I have to say, it's done all the time. In fact, it has to be done. You get, so the problem is solve as the best possible solve, I'll put quotes, AX equal B when there is no solution. And of course, what does that mean? B isn't in the column space. And it's quite typical if this matrix A is rectangular, maybe I have m equations, and that's bigger than the number of unknowns, then for sure the rank is not m. The rank couldn't be m now. So there will be a lot of right-hand sides with no solution. But here's an example. Some satellite is buzzing along. You measure its position. You make 1,000 measurements. So that gives you 1,000 equations for the parameters that give the position. But there aren't 1,000 parameters. There's just maybe 6 or something. Or you're measuring you're doing questionnaires. You're measuring resistances. You're taking pulses. You're measuring somebody's pulse rate. Okay, there's just one unknown, the pulse rate. So you measure it once, okay, fine. But if you really want to know it, you measure it multiple times. But then the measurements have noise in them. So the problem is that in many, many problems, we got too many equations, and they've got noise in the right-hand side. So AX equal B, I can't expect to solve it exactly right, because I don't even know what the error, there's error, there's a measurement mistake in B, but there's information too. There's a lot of information about X in there. And what I want to do is like separate the noise, the junk, from the information. And so this is a straightforward linear algebra problem. How do I solve? What's the best solution? Okay. Now, let me, I want to say, so that's like describes the problem in an algebraic way. I've got some equations. I'm looking for the best solution. Well, one way to find it is, one way to find a solution is throw away equations until you've got a nice square invertible system and solve that. That's not satisfactory. There's no reason in these measurements to say these measurements are perfect and these measurements are useless. We want to use all the measurements to get the best information, to get the maximum information. But how? Okay. Let me anticipate a matrix that's going to show up. This A is typically rectangular, but a matrix that shows up whenever you have, and chapter 3 was all about rectangular matrices. And we know when this is solvable, you could do elimination on it, right? But I'm thinking, hey, you do elimination, and you get equations 0 equal other non-zeros. I'm thinking elimination is going to fail. So that's our question. Elimination will get us down will tell us if there is a solution or not, but I'm now thinking not. Okay, so what are we going to do? All right, I want to tell you to jump ahead to the matrix that will play a key role. So this is the matrix that you want to understand for this chapter 4. And it's the matrix A transpose A. Tell me some things about that matrix. So A is this m by n matrix, rectangular. But now I'm saying that the good matrix that shows up in the end is A transpose A. So tell me something about that. Is it, yeah, tell me, what's the first thing you know about A transpose A? It's square, right? Square, because this is m by n, and this is n by m. So this is, the result is n by n. Good. Square. What else? It's symmetric. Good. It's symmetric. Because you remember how to do that. If we transpose that matrix, let's transpose it. A transpose A. If I transpose it, then that comes first, transpose. This comes second, transpose. And then transposing twice brings it back to the same, so it's symmetric. Good. Now, we now know how to ask more about a matrix. I'm interested in, is it invertible? If not, what's its null space? So I want to know about, because you're going to see, well, let me even, well, I shouldn't do this, but I will. Let me tell you what equation to solve when you can't solve that one. The good equation comes from multiplying both sides by A transpose. So the good equation that you get to is this one. A transpose A x equals A transpose B. That will be the central equation in the chapter. So I think, why not tell it to you? Why not admit it right away? Okay. I should really give x, I want to sort of indicate that this x isn't, I mean, this x was the solution to that equation if it existed, but probably didn't. Now, let me give this a different name, x hat, because I'm hoping this one will have a solution. And I'm saying that it's my best solution. I'll have to say, what does best mean? But that's going to be my plan. I'm going to say that the best solution solves this equation. So you see right away why I'm so interested in this matrix, A transpose A, and in its invertibility. Okay. Now, when is it invertible? Okay. Let me take a case. Let me just do an example, and then I'll just pick a matrix here, just so we see what A transpose A looks like. So let me take a matrix A, 1, 1, 1, 1, 2, 5, just to invent a matrix. So there's a matrix A. Notice that it has m equal 3 rows and n equal 2 columns. Its rank is, the rank of that matrix is 2, right? Yep, the columns are independent. Does AX equal B? If I look at AX equal B, so X is just X1, X2, and B is B1, B2, B3. Do I expect to solve AX equal B? What's, no way, right? I mean, linear algebra is great, but solving 3 equations with only 2 unknowns, usually we can't do it. We can only solve it if this vector B is what? I can solve that equation if that vector B1, B2, B3 is in the column space. If it's a combination of those columns, then fine. But usually it won't be. So the combinations just fill up a plane, and most vectors aren't on that plane. So what I'm saying is that I'm going to work with the matrix A transpose A. And I just want to figure out, in this example, what A transpose A is. So it's 2 by 2. The first entry is a 3. The next entry is an 8. This entry is a, what's that entry? 8, for sure. We knew it had to be. And this entry is, what's that now? Getting out my trusty calculator. 30, is that right? 30. And is that matrix invertible? There's an A transpose A. And it is invertible, right? 3, 8 is not a multiple of 8, 30, and it's invertible. And that's the normal, that's what I expect. So, this is what I want to show. So here's the key point. The null space of A transpose A, it's not going to be always invertible. Tell me a matrix, yeah, now I have to say that I can't say A transpose A is always invertible, because that's asking too much. I mean, what could the matrix A be, for example, so that A transpose A was not invertible? Well, even could be the zero matrix. I mean, that's like extreme case. Suppose I make this rank, suppose I change to that A. Now I figure out A transpose A again, and I get, what do I get? I get 9. I get 9, of course, and here I get, what's that entry? 27. And is that matrix invertible? No. And why do I knew it wouldn't be invertible anyway. Because this matrix only has rank 1. And if I have a product of matrices of rank 1, the product is not going to have a rank bigger than 1. So I'm not surprised that the answer only has rank 1. And that's what always happens. That the rank of A transpose A comes out to equal the rank of A. So, yeah, so the null space of A transpose A equals the null space of A. The rank of A transpose A equals the rank of A. So, I'll tell you as soon as I can why that's true, but let's draw from that the fact that I want. This tells me that this square symmetric matrix is invertible if, so here's my conclusion. A transpose A is invertible if, exactly if this null space is only got the 0 vector, which means the columns of A are independent. So A transpose A is invertible exactly if A has independent columns. That's the fact that I need about A transpose A. And then you'll see next time how A transpose A enters everything. Next lecture is actually a crucial one. Here I'm preparing for it by getting us thinking about A transpose A. And its rank is the same as the rank of A, and we can decide when it's invertible. Okay, so I'll see you Friday. Thanks.